Have you ever just stood outside, looked up at a massive commercial airplane zooming overhead, and honestly wondered, how on earth does something weighing hundreds of tons actually stay up there, right? Or maybe you've watched a rocket launch, just thousands of pounds of metal blasting upward on this literal pillar of fire, and tried to wrap your head around the sheer mechanics of it all. I mean, it kind of feels like it completely defies the laws of physics. But really, it's the absolute mastery of them.
Welcome to The Explainer. Today, we're diving into the exact field that answers those wild questions. We're stepping into the fascinating world of aerospace engineering. This is all about managing extreme margins of error. It's that ultimate intersection where raw, boundless human imagination meets the super rigorous laws of science. It's literally where we build the impossible.
Section 1, Wonder to Science. Let's ground all that wonder into a concrete definition.
So, at its core, aerospace engineering is the study of designing, building, testing, and, constantly improving vehicles that fly. And we're talking about a massive, incredibly diverse spectrum of vehicles here. Everything from everyday autonomous drones zipping around complex urban environments to your standard commercial passenger jets, all the way up to massive spacecraft built to travel far beyond Earth and achieve orbital velocity. But actually making these incredible machines fly, well, that's not just a simple matter of fluid dynamics. It takes a massive, highly coordinated effort across a really multidisciplinary field. Think about it. You can't design an engine that escapes Earth's gravity unless you have material scientists inventing entirely new alloys that can withstand the insane heat. Every successful flight you see is the result of thousands of engineers solving a giant puzzle together. They're bridging theoretical physics, advanced math, computer programming, electronics, and cutting-edge manufacturing. It's the whole shebang. Moving on to Section 2, Earth versus Space. Let's break down how this massive field is divided into two main branches based entirely on the extreme environments they operate in.
The first branch is aeronautical engineering. This area is completely focused on aircraft that operate right here, within Earth's atmosphere. So they deal directly with the complex fluid dynamics of the air around us. The engineers doing this have a very clear set of goals. They want to make the airplanes and helicopters we rely on every day faster, drastically safer, quieter for our communities, and way more fuel efficient. Basically, the atmosphere itself is their laboratory.
On the flip side, we have astronautical engineering. This branch looks upward and outward, focusing entirely on vehicles traveling out into the vacuum of space. Astronautical engineers aren't just dealing with the lack of air, right? They have to engineer for extreme temperature swings, super complex orbital mechanics, and managing closed-loop life support systems in a completely hostile environment. Their day-to-day involves creating rockets, satellites, and space stations, and mapping out those future missions that will eventually take humanity back to the moon, to Mars, and beyond. And this really illustrates the core dichotomy of the entire profession. It's essentially a tale of two mediums. You've got aeronautics, which is mastering the fluid dynamics of our atmosphere to perfect the airplane, versus astronautics, which is engineering for the absence of an atmosphere to launch rockets and spacecraft. They are two radically different operating environments requiring completely different solutions, but they're absolutely unified by our human desire to push past our earthly limits. Section 3, Solving the Gravity Problem. Because no matter which branch you're in, every single design is fundamentally a high-stakes battle to escape Earth's gravity. So the really crucial point here is that ultimate balance between weight and strength. Engineers actually call this the tyranny of the rocket equation. Basically, every extra kilogram of weight you add demands exponentially more fuel to lift it. But if you need more fuel, well, that fuel adds more weight. That drags down your overall thrust-to-weight ratio. It's this vicious cycle where the propellant itself becomes the main payload you're trying to lift. So engineers are constantly fighting this battle to keep the vehicle incredibly light without sacrificing any structural strength. Weight is absolutely the ultimate enemy here. To win this battle, engineers can't just rely on standard metals anymore. Instead, they turn to lightweight composite materials, like carbon fiber reinforced polymers and advanced titanium alloys. These are materials specifically engineered at the microscopic level to handle immense stress and extreme atmospheric pressure, but without the heavy, debilitating mass of traditional steel or aluminum. And that's exactly how we can build vehicles big enough to carry hundreds of people, but keep them surprisingly lightweight. Okay, but once you've built this light, super strong vehicle, how do you actually push it through the sky? Well, aeronautical propulsion often relies on a simple four-step process. First, the engine rapidly sucks in and compresses outside air. Second, it mixes that compressed air with jet fuel. Third, it continuously ignites that highly volatile mixture. And fourth, that continuous combustion blasts out a massive stream of high-speed exhaust backward, which generates the forward thrust needed to fly. It's this beautiful, continuous loop, but it completely relies on having a nice, dense atmosphere to pull air from. Now, here's where things get really interesting when you compare jets to rockets. While jets rely on pulling in atmospheric oxygen to burn their fuel, rockets operate out in space. There is no air. Because of that, rockets literally have to carry their own chemical oxidizer, something like liquid oxygen, to mix with their fuel. This makes them entirely independent of their environment. By combining fuel and oxidizer on board, they can blast out massive thrust without needing outside air, powering them straight through the vacuum of space.
Let's zoom out a bit for Section 4, the future of aerospace. Because modern aerospace is evolving right now at absolute breakneck speeds.
We are living through some massive, real-time transformations. Artificial intelligence, for example, isn't just crunching flight data anymore. It's what powers the real-time algorithms that let us autonomously land and recover reusable rockets. And those reusable boosters? Total game changer. They are dramatically lowering the cost of space travel per kilogram. Meanwhile, back down here on Earth, autonomous drones are completely transforming industries, from navigating complex urban layouts for rapid emergency responses to completely changing how we do precision agriculture.
But what's coming next is even more wild. On the horizon, scientists are actively developing low-emission electric aircraft for a greener future in our skies. We're talking about hypersonic vehicles capable of traveling Mach 5 and beyond, handling insane aerodynamic heat to shrink global travel times down to just a few hours. And of course, engineers are meticulously designing the deep space vehicles that will eventually carry human beings to the surface of Mars. Which brings us to a really exciting possibility. Because of all this rapid innovation, we're looking at a near future where taking a trip to space could be a perfectly routine experience for ordinary people. Imagine booking a flight not just to another country, but into orbit. It's no longer just science fiction. It's an active, working engineering roadmap. Finally, Section 5, the next impossible idea. Now, in aerospace engineering, math and physics are definitely the foundation. But curiosity is the engine. It's all about pushing the limits of what humanity believes is possible. Every question you ask about flight, about space, or about technology could honestly become the foundation for tomorrow's greatest breakthrough. Because at the end of the day, aerospace isn't just about putting together composites and rocket fuel. It's about staring down a fundamental limit of physics, like the sound barrier or Earth's escape velocity, and deciding you're going to engineer a way right through it. It's about expanding human potential.
I really want to emphasize this incredible thought from our source material. Every aircraft that crosses the sky and every spacecraft that explores the universe began as someone's impossible idea. Think about that. The massive passenger jets, the rovers driving around on Mars right now, the satellite constellations connecting the globe, literally all of it started as nothing more than a crazy dream in the mind of someone who just refused to accept gravity's final word. The tools are out there right now. This field is advancing faster than it ever has before. The vacuum of space and the skies above are just waiting for the next great innovator. So the only question left for you is, what will your impossible idea be? Keep questioning, keep learning, and I'll catch you in the next explainer.